Hey guys, let's learn about simple harmonic motion. To begin with, the definition of simple harmonic motion is simply that the acceleration is proportional to the position. The main situations where you're going to observe simple harmonic motion are for a mass on a spring, a simple pendulum, and what's called a physical pendulum, which is where it's a mass distribution where you can't claim that, say, all the mass is located at the end like you could for a simple pendulum. So we have to be a little bit more formal, though, because this is AP physics when we're talking about the definition of simple harmonic motion. So acceleration is proportional to position in sort of more technical terms is going to look like, well, this differential equation that you see here. Now, the right side of this equation, of course, is just acceleration, the second derivative of position. The omega squared term in there is something that we're, at the beginning of this video, just going to leave sort of nebulous, like what is it? But we're going to introduce how it works in the form of the trigonometric functions which describe what simple harmonic motion looks like. So to begin with then, position for simple harmonic motion looks like this function here, right? Meaning, if you take a cosine function and you graph it out, it's this kind of a deal, right? It goes up and down and up and down. That's what simple harmonic motion is, right? Either up and down or back and forth, and it's going to follow something like a cosine. Now, if you've never seen a second order differential equation, which is what this is, right? It's second order because there's a second derivative involved in it. Just know the AP is not going to actually make you solve a second order differential equation in the same way that we've, say, solved first order differential equations for something like drag forces. They don't expect you to actually know how to solve it. But I do want you to understand why this works the way it does. So what I'm going to do is I'm going to take this position function that we've got, and we're going to take the derivative twice, and then you're going to see something really interesting happen. If we take the derivative once, we get this velocity function. And notice the omega that appears here due to the chain rule, and of course the negative and the sign because the derivative of cosine is negative sine. Taking the derivative again, we now have the function for acceleration. All right, so that's nice and all, but like, so what? I can take a derivative any number of times I want. Well, something really amazing happens here. Remember, the definition of simple harmonic motion, the formal definition, is this thing up here, meaning any situation in which you can say that the second derivative of position is equal to the original position function times some constant omega squared with a negative sign stuck on the front of it. Any physical situation which can be modeled in this way is going to be simple harmonic motion. And if we look at our function for the acceleration, notice that we have a and cosine omega t appearing in it all over again, which is the position function that we started with. All right, so take that out, and we could express that the acceleration equals negative omega squared x. All right, which is that's what we set up here because d squared x dt squared is the acceleration. So the acceleration function is equal to the position function times negative omega squared. All right, now, what is omega? Well, what omega is depends very strongly on the type of simple harmonic motion that you are seeing. Omega is referred to as the angular frequency. All right, not to be confused, of course, with angular velocity. Okay, but it's the same symbol for reasons that'll become very clear in a little bit. So because the identity of omega depends very strongly on what type of oscillation we've got going on, we need to look at a few specific examples. And we said we're going to do springs, pendulums, and physical pendulums. So the spring is the easiest one to work with. So we'll start with that one. Normally, when we're looking at a vertically oscillating spring, like meaning before we've learned how simple harmonic motion works, we talk about x equals 0 being, up here, the unextended length of the spring, and then, this position is x equals something, and this would be the special equilibrium position, right, where mg equals kx, and it could just hang there, and then, it would be down there. And of course, when it's oscillating, it would oscillate evenly between these two positions. Well, when we're talking about harmonic motion or oscillation, we will instead define x equals 0 as the equilibrium position. This might be a little bit counterintuitive, but what it actually allows you to do is not have to fuss around with exactly where x is if you say, change the amount of mass that you've got on your spring. More mass would lower the equilibrium position, and it would change the frequency of the oscillation. But what we usually care about is, say, the amplitude relative to this middle position. And so therefore, for the purposes of oscillation, we will call this x equals 0. All right, now it's still true that you can use this relationship to find out what the equilibrium position is relative to the unextended spring, and you will still have to do that. But for the purposes of describing just the oscillation, we'll talk about the equilibrium position always as being x equals 0. Therefore, if x equals 0 is the middle position, then the top position would be x equals, say, positive a, where a is for amplitude, and the bottom position would be x equals negative a. It is always true for any type of harmonic oscillation that you get the maximum acceleration when the position from equilibrium is the greatest. It's also always going to be true that the direction of the acceleration is opposite of the displacement, again, relative to what you call the equilibrium position, right? Anywhere above equilibrium, the acceleration is down. That would be a negative acceleration when it has a positive position. And of course, when it's at the bottom, the acceleration is in the upwards direction, again, opposite its position. Finally, we should also note that you have always the maximum velocity when the position is 0. So it's always moving fastest right here at the equilibrium position. If you're expected to sketch or, match up graphs of position, velocity, and acceleration for simple harmonic motion, it might be useful to know, the A cosine omega t stuff that we wrote down earlier. And so we're going to sketch out a few of those graphs. So there's our position function, where A, if you recall, is the amplitude. That would be the maximum height of your cosine function. And then the omega here is our angular frequency. That's going to relate to how packed together your sort of waves are in your cosine function. And after we've drawn these three graphs, we're going to talk about what's called the period of motion and how that relates to omega. Note when you draw the velocity function, you need to make sure that you carefully line up the peaks and valleys. Also be careful with the sign of your velocity. Remember, it's the derivative. So that means that initially the velocity would be 0 because this is flat. At this moment, the velocity would be negative, very negative, right, or the most negative. Here we're back to 0 again, that's this spot. And it goes on and on like that. So it's 90 degrees out of phase. And of course, our acceleration is 180 degrees out of phase with the position graph, right? It's going to look more or less like you took the position graph and you flipped it over. The magnitude of it will be a little bit different, though, because there's the amplitude for your acceleration function. So putting it all together, if you've got, say, a graph like this, the period of oscillation is found by picking two identical moments on your graph and looking at, all right, what is the, amount of time between those two positions? That's the period. And the period is related to this angular frequency function by 2 pi over omega. You guys should be familiar with the fact that, a cosine or sine function repeats every 2 pi radians when it's just something like, cosine of theta, right? That repeats every 2 pi radians. But if you have it as like cosine of 2 theta, then it repeats twice as frequently. The 2 in there would be your angular frequency. And in this case, cosine 2 theta would tell you the period would be, I guess, pi seconds or something like that. Also notice when you're looking at a graph, if you can pick off the max velocity value, right, then you can also relate that back to the amplitude and the angular frequency based on the maximum value for your velocity function being a omega, because it was negative a omega sine omega t. You can do the same thing with a velocity function. The acceleration function. The maximum acceleration is a omega squared. Okay, so then what exactly is omega if we're looking at a mass on a spring? We're going to derive this for a horizontally oscillating mass so that we can ignore the problem of what about the force of gravity. So if it's a mass on a spring, the only force acting on it horizontally would be the spring force and potentially the force of friction. The spring force is going to be to the left anytime the position is off to the right. Anytime it's off on the left in terms of its position, the spring force is going to be to the right. That's because the acceleration is always in the opposite direction of its motion. For some of these questions, they might throw in friction. If there's friction, be careful with the direction of friction. Friction won't necessarily be opposite the spring force. It's opposite the direction of motion. Okay, so if it's off to the right, it could be moving this way, or it could be moving back towards equilibrium. So be careful. Friction could point in either direction. It's just going to be opposite the direction of motion. If there is friction, by the way, this is what we call damped oscillation. The position versus time function, instead of being like a nice, sine or cosine, is going to, peter out to nothing like that. Now, if we turn this into a forces equation and assume there's no friction, we're going to have just negative kx equals ma. The negative sign from Hooke's law is actually essential this one time because, remember, for it to be simple harmonic motion, oops, that negative sign should not be there. For it to be simple harmonic motion, you need to have negative omega squared x equals dx squared dt squared, right? The negative must be there because the position and the acceleration have to be in opposite directions. So the negative is actually essential for showing that simple harmonic motion occurs. Our next line down, what we've done is, solved for acceleration, but then also replaced it with a differential, so that now this is a differential equation. This is what you write if they say, write a differential equation showing simple harmonic motion. Okay, at this point, you're actually done. You have proved by writing this that simple harmonic motion occurs. If you're looking at that, though, and you're like, I'm not sure I see, how does this match up with that right there? Well, it's got all the right form. You've got your negative sign. You've got something in front of the x. That something, by the way, is always your omega squared for your situation. Okay, and then we've got x, and we've got second derivative of x. It fits, it works, that shows simple harmonic motion will occur. Probably the hardest part for most people to wrap their heads around for this is exactly what omega is or why it is that, or the weird step where we're like, yeah, and so K over M is omega squared. Like, okay, what does that even mean? Well, what it means is that you can use the spring constant and the mass to determine the frequency of an oscillation. Also, remember, whatever is between the negative sign and the x is not omega, but omega squared, which is why we're saying that omega is the square root of K over M for an oscillating spring. In fact, whether it's oscillating horizontally or vertically. So that means that if you were writing a position or acceleration equation for something that was undergoing harmonic oscillation, what you would plug in right here for omega would be root K over M. That's what would go in there. Also, if you're trying to determine the period for an oscillating mass on a spring, because it's 2 pi over omega, and omega is root K over M, you can get the period from, well, plugging that in, and there it is. That equation, by the way, is given to you on the AP equations sheet that you'll be provided on the day of the exam, so you will not have to memorize that. But you will need to learn how to show that simple harmonic motion occurs, just in case they give you something like that on the AP test. All right, let's look at another situation. The simple pendulum. There it is, nice and simple. Okay, the not so simple part about the simple pendulum is recognizing that it's actually a tilted axes problem. I don't think it's that crazy. You should be able to see, oh, it accelerates always perpendicular to the tension, so it makes sense to tilt your axes. Also note that the acceleration is constantly changing. Well, that's a property of simple harmonic motion. Acceleration changes with position, so yeah, the more tilted it is, the greater the acceleration. That sounds like it could be simple harmonic motion. But I'm not really seeing how this is going to turn into our, I keep having that negative sign there. I'm not seeing how it's going to turn into our definition of simple harmonic motion. What? How does this happen? Well, one thing is it doesn't necessarily have to be actually x in these two spots. It could be theta. All right, that might give you a sense of where we're going with this. The next step is you have to replace linear acceleration with angular acceleration. This is coming to you from the equation A equals alpha r. Remember that one? And so r would be the length of the pendulum, therefore alpha times L is your linear acceleration. So we'll just sub that in. And now the voodoo. One problem that we were going to have is that this is a sine theta and not just a theta. If it had just been a straight up theta, everything would have been cool because if you say what's the second derivative of theta, well, that's alpha, right? No problems there, but this says sine theta. So somehow that's got to turn into a theta. And the voodoo magic here is what's called the small angle approximation, which says that sine theta is about equal to theta as long as theta is small. Now, if you're like, that sounds like garbage. No, it's not so crazy. Draw a graph, if you like, of y equals x. Okay, draw a graph of sine of x. Okay, doesn't work for like out here, but it works reasonably well for if you're in that region. That's what the small angle approximation says. If you don't believe me, try out your calculator, go to radian mode and type in like sine of 0.5, and you'll discover that it's reasonably close to 0.5. It gets better and better as the numbers get smaller. So if you type in like sine of 0.1, it's really actually very close to 0.1. And so we will replace sine theta with theta under the assumption that theta is small. So as long as a pendulum is not oscillating over like, 180 degrees or something, then the small angle approximation works great and it'll be simple harmonic motion. If you are oscillating over much greater angular displacements, then it stops being a good approximation and it stops resembling simple harmonic motion. But as long as theta is like less than 1 radian, it works. Okay, only a little bit left to do. We just need to replace alpha with the second derivative of theta. Wait a minute, there's a negative sign here. Okay, now remember, you have to have, gosh darn it, you have to have a negative sign in order to make this work. There has to be a negative there. And our defense of why it needs to be there is not just going to be because I need there to be a negative. It's, well, listen, the angular acceleration is always in the opposite direction from the angular displacement, right? Makes good sense. Okay, moving on. So yeah, there needs to be a negative one way or the other. If you can't think of why it is, just throw it in there. You're going to have a negative. And boom, this is enough to prove simple harmonic motion. Okay, but what is omega squared? Everybody take a moment, think about what you should have learned from the previous example. What is omega squared? Pause and think. That's right, it's the G over L part, the bit between the negative and the theta. That means that the period would be 2 pi times root L over G, because 2 pi over omega. Also, that equation is provided to you on the AP equation sheet as well, so you don't need to memorize that, but if they ask about a simple pendulum, you ought to know this process. A little bit more complicated than it was for a spring, but still the same kind of idea. When we want to determine the equation for simple harmonic motion of what's called a physical pendulum, it's going to look a little bit different from either of the other two, but it will use a lot of the same stuff that we did for a simple pendulum, such as the small angle approximation. So here we, though, have to begin with torque. Remember, the idea for torque is it's a cross product, right? F cross R. The weight of the pendulum would be the bit that makes it oscillate, and the pivot point always has to be some distance away from the center of mass, because if you put it at the center of mass, it wouldn't oscillate. So the pivot's always got to be some distance of d away. Therefore, the torque is, all right, there's your F, there's your R, and the sign is there because it's a cross product, and therefore it depends on the value of this angle between the radial vector and the force vector. The sum of the torques always equals I alpha. Just like we did with the simple pendulum, we will now replace sine theta with theta using the small angle approximation, solve the equation for alpha, and replace alpha with the negative second derivative of angular position, theta, because we need that negative sign there. Okay, so what is omega for a physical pendulum? Again, pause, think about it. What is omega? Well, since omega squared is, gosh darn thing, always the bit between the negative sign and the whatever kind of position, omega must be the square root of mgd over I. Please note the I is never just one of the simple equations that you look up in a table for solids. It's always going to be something from parallel axis theorem, because the object literally can't be oscillating through its center of mass. It wouldn't oscillate. It would just sit there. Okay, so it's always got to be something from parallel axis theorem. Fortunately, this D and this D represent the same thing. They are both this distance. Okay, so easy enough. ICM would depend on whatever the shape is, and then D is the distance between the center of mass and the pivot point. And there's our equation for the period of a physical pendulum. That equation, by the way, is not given on the AP equation sheet. Sorry, they don't give you all of them. This one you would have to derive. Now, to prepare for the AP, I would say practice this a couple of times, especially for the simple pendulum and the physical pendulum. There's not a lot to practice with the spring, but these last two probably take a little bit more practice just to make sure that you've got the basic idea down and remember it. The likelihood that there's going to be a free response question that's like nothing but harmonic oscillation is pretty low. Usually there's just going to be a little bit of it mixed in, and often it's just going to be something like determine the period of oscillation for this weight, something like that. And so there's not really any really like harmonic oscillation stuff that's going to happen. It's just going to be a simple like find the period or something like that. They do, however, occasionally have something like a lab-based problem for these. So I wanted to give you a glance at how one of those might go. So typically it would be something like this. They tell you, here's in this column the period of oscillation for a mass on a spring, and as a function of mass. So it's period, mass, and you've got all these paired values. And if you graphed them out as is, you would not get a straight line. And remember, for the lab problems, the game is always linearize it. It has to be a straight line, and the slope is going to tell you something. So t versus m, worthless. Okay, think for a moment. Based on the equation that you have here for the simple harmonic motion of a mass on a spring, what things could you graph to get a straight line? Think. If you thought this, then good. You also, by the way, could do like period versus the square root of m. That also works, right? Either of those is fine. But I would say a lot of the time t squared versus m ends up being the easier thing to graph for a variety of reasons. And if you have done it this way, then that means that the slope is 4 pi squared over k. To understand how we got that, imagine taking this equation here and square both sides. You're going to get this, the slope function here, times m on the right side. Okay, so that means if m is your x values, then 4 pi squared over k is your slope, because t squared is your y values. The other classic place where you'll definitely see some simple harmonic motion will be on the multiple choice. It's often just straightforward stuff such as this one. Right? They tell you, oh, the period's this when the length is this. What if we double the length? What's that going to do to the period? All right, well, stop and think about this. If it's a simple pendulum, look back at the equation for a simple pendulum. And the conclusion that you would come to is probably, definitely should be, C. Doubling the length does not double the period because the period's not proportional to length, it's proportional to the square root of L. Okay, or you could say it that way as well. So that means doubling the length only gives you root 2 times the original period of the pendulum. Okay, well, I hope that was informative. I guess the only other thing that I would want to add that just occurs to me here is for the simple pendulum, I think it's really interesting to note that mass is not part of this equation. Doesn't matter how heavy the pendulum is, just matters what's the length of the arm, and okay, also what is the local gravity. Okay, so you can use a pendulum to determine what the local gravity is, because it doesn't matter what the mass of the object is, just length of pendulum, which is easy to measure, and then whatever the local gravity may happen to be. There we go. All right, I hope that is an informative and helpful guide to simple harmonic motion. Practice a little bit the derivations, try it out on a couple of different AP free response questions that you can find posted on the AP website, and you'll get the hang of it probably much sooner than you think you will. Okay? All right, guys, this was good. I think I'm going to end the video here while I'm ahead. All right, see ya.